example, just some power calculations to look at the average real power and the reactive power. This is a network that's illustrated. We've got this terminal pair. We are given the voltage and current as functions of time, each with their respective phase angles. So let's look and see how we might do that average and reactive power calculation. So first, we're going to calculate P and Q directly, and let's look and see what these equations are referring to. Actually, the first thing we have to do is you're given here a sine and a cosine, and so remember, everything we do in AC circuits is done with respect to the cosine function. So the first thing we have to do is convert this sine to cosine, and that's just something to pay attention for. I normally in a test would not introduce, tricky questions, but I have been known to do so. So you introduce that minus 90 degree phase shift to change from a sinusoid to a cosine, and now we have the current as a cosine. And so we can just calculate the average power and the reactive power directly from the two equations, and let's go back and look at what those are. Right here. So the average power is the voltage magnitude times the current magnitude divided by 2 multiplied by the power factor. And the reactive power is the same magnitude multiplied by the reactive power. So let's go back. So that's what these two formulas are. This is the voltage magnitude, the current magnitude, 1/2 cosine of theta V minus theta I. If you do that calculation, you get minus 100 watts. Do exactly the same calculation, only finding the sine, you get 173.21 bars. So question is this inductive or capacitive? Let's go back. We have cosine of minus 105. We have for the voltage, so let me so for the current, it's minus 105. For the voltage phase angle, it's 15. So let's draw our complex plane. The voltage is here at 15 degrees. The current is here at 105 degrees. The voltage is leading the current, okay, because it is 120 degrees ahead in a clockwise rotation, or the angle that is less than 180 degrees. So voltage leads the current. Q is positive. Our load is inductive. So two different ways to know this. First of all, if your reactive power is positive, you have an inductive impedance. If your voltage leads the current, you also have an inductive impedance. So there's P and Q. So easy, literally plugging into the formula. Okay, I need to come out of screenshot mode for just a moment. Sorry, don't know what this is doing here. Let me end screen show and let me move my stuff around a little bit because I've got several things here on one page. Okay, so new topic. We completed the example, and now what we want to talk about is how this is different if we use RMS currents and voltages. So first of all, you need to know that I will always tell you if the voltage or current are RMS. In power systems, and if you go on to take some of Dr. Gieselman's courses in power systems and some power electronics courses, typically people use RMS voltage when they specify voltages. And they often, in power systems, will not tell you, it's just assumed. In circuits, we don't do that. If it's RMS, I'll denote it as being RMS. But it is standard to use RMS in power systems. So, for example, when you're told that your household runs on 120 volts or 110 volts, that is actually the RMS voltage. And if you were to hook up your power from your home to an oscilloscope and actually track a peak-to-peak waveform, you would not get 110. You would get 110 times the square root of 2. So RMS is commonly used in AC power discussions in courses that follow on past circuits. So basically, because the voltage and the current are the equivalent of quote unquote DC. In other words, we were told that the RMS voltage delivers the same energy over time that a sinusoidal source of the original magnitude of the voltage would deliver. So because of that, it's easy to calculate the average power if you already have the voltage in terms of RMS and if the impedance is resistive. So we can just, if we have this kind of circuit, we can calculate the average power dissipated in that resistor either by taking the RMS voltage squared over R or by taking the RMS current squared times R. And we, in this book, as well as in other books, the terms effective and RMS are used interchangeably. So this would be an equivalent load, this would be a voltage, and you could get the RMS voltage by taking what? Vmax over the square root of 2. How do we know that formula? We learned it in the last chapter. It only applies for sinusoidal currents and voltages of single frequency. All right, so as we know, the effective value of V sub S delivers the same power to the resistor as the DC voltage. So it would be like, to use RMS, we replaced it with a DC source as far as average power is concerned. And so we can do a calculation of the average power by taking our original formula for average power and separating this out into two parts, Vm over the square root of 2 and Im over the square root of 2. And that ends up being Vrms, Irms times the cosine of theta V minus theta I. So these are alternative formulas for P and Q if voltages and currents are given as RMS or effective voltages. And notice the only thing that's missing is the 1/2. Okay, so some additional definitions, and these are useful, especially if you are working in the phasor domain and you have everything already in the phasor domain. You can make some of these, you can calculate some of these quantities a little easier, and they also give you a little more insight into what's going on with power in the circuit. So the first thing that we do is we introduce and define the concept of complex power. The complex power is basically the complex sum of real power and reactive power. So remember, P is our real power, Q is our reactive power. Complex power is defined as P plus JQ. So it is a complex quantity. Sorry. Okay, so complex power has units of volt amps. Average power has units of watts. Reactive power has units of bars. So average power is P, reactive power is Q, complex power is S. Once again, this is a plug into the formula kind of calculation. Once you know P and Q, you can easily find S. So there's some kind of interesting things that complex power does for us. It defines a geometric relationship between different power quantities, and this is what we refer to as the power triangle. This is a little bit of an old-fashioned concept, but it's important because first of all, this shows up on a fairly regular basis on the EE fundamentals exam for licensure. So once you learn it, you should be able to sort of visualize it in your brain from now on, so that when they talk about power triangles, you get a feeling of what they're talking about. So basically, you can make a triangle where the average power forms the horizontal leg, the reactive power forms the vertical leg of the right triangle, and the magnitude of the complex power, which is referred to as a parent power is the hypotenuse. If you were visualizing this on a complex plane, then this would be a phasor S. So this is the phasor S, but its length is the magnitude of S. Theta is the phase difference between the reactive and the average power. So what's kind of cool about this is if you have a load, and it's complex, so you have a resistance and a reactance, so you have a complex Z, an impedance, then the power, and you calculate the power through that load, the ratio of Q and P in the power triangle is going to be the same as the ratio of the reactance X and the resistance R. So the complex and average power, or the reactive and average power, reactive power and average power have the same ratio as the reactance of the impedance and the resistance of the impedance. So you can get an idea, if you have an only resistive load, then the Q side of your triangle goes to 0, and you'll have only average power. If you have only a reactive load, then the Q side becomes a maximum. Theta goes to 90 degrees, and the average power shrinks down to 0. So it's kind of cool because basically they form similar triangles. Theta is the phase difference. It's the power factor angle, the difference between the voltage and current. So it gives you some idea of how close you are to 1 with your power factor by looking at the power triangle. So apparent power in the previous diagram from the Pythagorean theorem can be calculated by the square root of p squared plus q squared. Like complex power, it's measured in voltamps. It tends to be a pretty useful concept. Apparent power represents the volt-amp capacity required to supply the average power used by the device. So unless the power factor is 0, you have to have a higher volt-amp capacity than average power so that the device produces the average power you want. So this is what I was talking about earlier, that you will often find things that are rated with a power factor. That gives you an impression, if I actually really want 10 kilowatts, then probably the thing that's providing it and the load need to be such that I've got more than 10 kilowatts so that my average power is what I want. So if you end up being a power person and you take those courses, you'll learn all of that stuff in power systems. So if we use the RMS values of the sinusoidal current and voltage, then we use phasor notation, then S can be represented as VRMS, IRMS times the angle theta V minus theta I. So S can be represented in polar or phasor form in the following way if V and I are RMS. If they're not RMS, then basically you have to, you can substitute for the magnitude in terms of RMS to get that from S. The original expressions for P and Q that gave you this P and this Q can either use RMS or magnitude. It just depends on which formula you use. So the point is, you can calculate S directly. If you have V and I already in phasor form, you can calculate S directly. What this will give you is a complex number. If you convert it to rectangular notation, P and Q come out of that directly. So this would be representative of a circuit that looks like this, where you have some RMS voltage and RMS current. So continuing on here, VRMS, IRMS times angle theta V minus theta I can be written in its exponential form. And then you can separate out this exponent to have a theta V part and a theta I part. Now remember, originally our voltage had a phase angle of theta V and our current had a phase angle of theta I. So in calculating the complex power, We have the original phase angle of the voltage, but we have negative phase angle of the current. The way to obtain that, anytime we have a complex number that has a magnitude that is the same, but a phase angle that is negative, the original, then that is the complex conjugate of the original complex number. So when the phase changes from a positive to a negative phase angle in an expression, basically what you're using is the complex conjugate. So we can write an alternate form for the complex power. Instead of P plus JQ, if we know the RMS, phasor, current, and voltage, we can use VRMS times I star RMS. And I star RMS is I RMS e to the minus J theta I. That comes directly from Euler's identities. If you're not using RMS, then this formula just changes to 1/2 VI star, where V and I are magnitude and value. So to sort of conclude this rather lengthy discussion of complex power and alternate formulas for the power, there are a number of formulas, some using current and voltage, some using P and Q, some starting from the time domain expressions for voltage and current, others working with the phasor domain voltage and current expressions. So as you go through this, you're going to find that in some of these expressions you have, as we have here, an RMS, and the bold would indicate that this is the phasor voltage. In other expressions, you'll have terms that are the magnitude. Notice the difference. This one's in bold. This one is the magnitude and carries with it a phase angle. So you just have to be careful because there are a lot of different formulas, all of which will give you the same outcome. Which one do you use? Some of it is personal preference. Is there one group of formulas that you would like to memorize and just utilize those in every calculation? Other times it's convenience or expediency. It might be easier and quicker to use one set of formulas over another. Okay, let's see. Yeah, here we go. This is what I said on the previous slide. If the voltage and current phasors are not specified as RMS values, then the formula would contain a 1/2, and V and I would be the magnitudes associated with your sinusoidal current and voltage. All of the expressions for S, P, and Q are using the passive sign convention. If the current reference, for whatever reason, in the direction of the voltage rise across the terminals, you need to put a minus sign into this equation, just like we did back when we looked at DC power. So here's an example. Actually, this is the same example where you started with the instantaneous expressions for current and voltage, but here's an example asking us to calculate average and reactive power at the terminals of a network where the voltage and current are given as phasor expressions. So we would just use the previous formulas. We would just use the previous formulas where we would take 1/2 VI star. So we would take 1/2 of 100 times 4, and then the angles would be 15 degrees. I star is plus 105, so the angle is theta I minus theta V. We should come up with exactly the same result that we had in the previous expression. So at this point, I will discard the annotations, and I want to go ahead and stop the video here. Future videos on this information will sort of incorporate some of the things we've already learned about AC signals, and we'll just show some example problems.